All right, so let's go and get started. Let me get the lights adjusted a little bit. Okay, I'm going to give you all just sort of a brief recap of what we did last time. We'll get into an example looking at how this vibration stuff works in here. But just to recap, we looked at the derivation of a single degree of freedom system. That is, we have think of it as a particle in space that resists motion by way of not only its stiffness, but its mass. Okay? And based on its initial conditions, we determined that its displacement is defined by the following. Its displacement being a function of time. Okay? Up until now, we haven't considered time. We haven't really cared about it. Now, it's starting to matter for these types of analyses. I talked a little bit about units. I'll move past that. And then we kind of briefly mentioned the stuff associated with single degree of freedom systems that we won't cover in this course, but I know my vibrations folks know all about, and the stuff that can make things kind of complicated. For instance, we describe this single degree of freedom system as a system that resists motion by way of its stiffness and its mass. But there's a whole host of other stuff going on, things like friction, air drag, and what have you. So usually that's expressed mathematically as a function of the system's velocity, and we call that damping. Okay. In addition, so if you have a damped system, your vibration dies out. It's, again, like a guitar string. You pluck a guitar string, it plays, but after a while it dies out. Okay, it loses that energy. Another issue is the loading. You know, for what we do in this course, we assume free vibration. In other words, the system vibrates under its own stiffness and mass, and that's it. Well, what about if we actually load the system, actually take it and shake it, or apply some impulse load, or what have you? Well, when we do that, that changes our response significantly. And we tend to have two types of assessments that we deal with, a forced response and a free vibration response. Now, from a simplistic standpoint, just to give you kind of an idea, if I take a system and I load it harmonically, kind of like, you know, in that wave-type fashion, depending upon the frequency, I can get some serious responses that will really affect things. For instance, we talked about last time the concept of a wine glass. If you take a wine glass, you've probably seen that famous image of either the lady or the guy singing in front of the wine glass, and they hit that pitch and the wine glass shatters. It's because their vocal, the vibratory waves that they are projecting from their vocal cords are vibrating at the same frequency as the glass. That's called resonance, and that's, you know, what happens. That's why, you know, this response curve just sort of shoots through the roof. All right. So what we then said is, all right, let's see if we can assess not only single degree of freedom systems, but multi-degree of freedom systems. And let's say if we can look at that from a finite element perspective. Okay? Now we started off, we said, all right, let's go back to what we did before. We calculated the internal energy and the external work done on a system. Now, what makes this kind of interesting is if we're doing a free vibration problem, there is no set of external loads, so the virtual work done outside is zero. So all we have is this. And this doesn't really make a whole lot of sense, because this is basically saying, well, if there's no load, there's no displacements. But that's not the case, because we know it's vibrating. That's because we haven't introduced the energy associated with its acceleration. So that's kinetic energy. Let's talk a little bit about kinetic energy. You all have had physics before. 1/2 mass times velocity squared. We can express that from a finite element perspective using our shape functions. Again, I'll admit I'm doing a little bit of magic from here to here. That results from Hamilton's principle. If you take a course in advanced vibrations, you will talk about Hamilton's principle at some point in there. For our purposes, it's just another way of deriving your equations of motion and another way of approaching that problem. Positives and negatives depending on the type of analysis you're doing. We can expand that out, and you know, we get a little bit more of an expanded version of our energy solution. We say, all right, let's take out those arbitrary displacements. They don't matter. And now it's starting to look a little more familiar. You know, have a pile of junk times the accelerations plus a pile of junk times the displacements equals 0. We already recognize this. That's the stiffness matrix. This unknown term Again, it's related to the inertia, to the acceleration. This is our mass matrix, okay? Excuse me. Now, in terms of solving this system, we saw last time that sine curves seem to make a lot of sense, so let's assume that our displacement is sinusoidal in nature. We need the function and then the second derivative because we're dealing with displacements and accelerations. Plug and chug. We factor out our trig terms, and we look at this, and this is where that eigenvalue problem comes into play. The only non-trivial solution we're going to achieve for this system that we see here is if the determinant of the quantity inside the parentheses equals 0, and that's our eigenvalue problem. Okay, so that's how we're going to assess that. Now, what I did just to be nice is I derived some mass matrices for you. So this is the mass matrix for a bar element. To give you an idea how it works, remember these are the shape functions for a bar element, n and n transpose. So n transpose times n, do the matrix math and all the algebra, the foiling and whatnot, and you get this, okay? Integrate those terms from 0 to L and multiply them times rho A, density times the area, and lo and behold, there's your mass matrix. That is the mass matrix for a bar. It's called a consistent mass matrix because you're using the same finite element theory consistently with what you've done before, okay? Sometimes a lumped mass matrix might make more sense, literally just lump them, all the terms along the main diagonal. There are advantages to that. It just depends on the type of problem that you're looking at, okay? But again, this isn't an advanced vibrations course. If you were taking that, you talk more about that stuff. In here, I just want to make sure you understand how to do the numerical, the grunt work, the calcs associated with the finite element approach. So here's for a two-noded bar. We already knew what the stiffness matrix was. Now we know what the mass matrix is. Remember, just like we did last time, you can convert that to a -1 +1 domain. You could also numerically integrate it, you know, all that jazz. I also decided to go ahead and just give you the mass matrix and stiffness matrix for a beam, okay? Instead of making you do all that, there's not really any point. It's just the same, you know, business as usual, all right? Here's the mass matrix. You all should be familiar with the stiffness matrix and so on and so forth. Everybody all right with that? Any questions? Any concerns? All right, so what I want to do is I want to do this example. Now, I'll admit I forgot to put this on your slides last time, and I'll explain what this is. So we're going to do this example together, so if you haven't opened Excel or whatnot, you might want to go ahead and do that. We're going to analyze this problem utilizing just one finite element, okay? So we have a beam. It's a cantilevered beam. It's made of steel, because that's my favorite material. E is 29,000 KSI. Now, my steel design folks should know this by now, that E is 29,000, and the unit weight of steel is 490 pounds per cubic foot. Okay, we'll say that this is a rectangular beam. It's just 3 inches wide and 6 inches tall. And basically what I'm asking, if it's 10 feet long, what I'm asking is, here's the beam. If I take a sledgehammer and I hit the end of that beam, it's going to vibrate. Okay, I want to know what its natural frequency is. Its frequency under free vibration. Now, this is a classic problem in the world of advanced vibrations, okay? You folks who are taking advanced vibrations, you should be able to solve problems like this by the end of the semester, if not already, okay, using an analytical approach. This is a cantilevered beam undergoing free vibration. If you haven't already done problems like that, you will, okay? Now, if you actually go through and do the math associated with free vibration for a problem like this, you get that the first natural frequency, the theoretical value, is around 3.52 times the square root of EI over rho AL to the fourth, okay? So what we're going to do is we're going to use that as our benchmark. We're going to compute the theoretical natural frequency and see if our finite element natural frequency stacks up, okay? Make sense? All right, everybody good? All right, so let's go ahead. Let me open up an Excel sheet, and we'll sort of work this through together. Okay, so what I'm going to do is I'm going to start off, let's do the easy parts associated with the beam. Let's do the geometric properties. So let me, let's do some geometric properties associated with the beam. For instance, we have a width of the beam and a height of the beam. How wide is this beam? 3 inches. There we go, 3 inches, and it's 6 inches tall, right? So the area is just going to be 3 times 6, right? All right, make sense? All right, that's the easy one. What about the moment of inertia? What's the moment of inertia of a rectangle? What's going on out there? What's the moment of inertia of a rectangle? There we go, BH cubed over 12. It's a rectangle. B times H cubed divided by 12. Y'all should know that, right? Okay. And how long is this beam? How long is it? 10 feet. So how many inches? There we go. Okay. Sound good? All right. Now let's look up some material. Now let's do some material properties. Oh. I changed something here accidentally. All right. First off, what's E? 29,000, right? What are the units? KSI, okay. That's going to be kind of important for what comes next, okay? So we really want to make sure that we're understanding that. So this is 29,000 KSI, okay? Most of what we're going to do in a little bit is pretty rote, but I want you to understand what's about to happen, okay? Now, what is the unit weight of steel? 490 pounds per cubic foot, right? So I'm going to call this, I'll just use Y because I don't want to type out gamma, pounds per cubic foot, and it's 490. Okay. Does that present a units problem? You bet, right? That's feet and pounds. That's not what we're dealing with. Let's start off, let's do some conversions, okay? How do I get this from pounds per cubic foot to kips per cubic foot? What do I do? Divide by 1,000, right? Sound right? So a cube of this, 1 cubic foot weighs 0.49 kips, right? Now, we got some issues because that's kips per cubic foot. What we really need, kips per cubic inch. Now, how many cubic inches are in a cubic foot? 12 times 12 times 12, right? So maybe what we need to do is take that and divide it by 12 cubed. So it's going to be a small number. But think what you're asking. You're asking how many kips does this much steel weigh? That's going to be a pretty small number, right? Make sense? Is that the density that we need? That's not a density at all. Density is related to mass. This is related to weight. What do I need to do to this number? We have to divide by gravity. Yeah, we have to divide by the acceleration due to gravity. So, let's look at gravity. Does anybody remember a number for gravity in U.S. units? 32.2 what? Feet per second squared. So, if I do feet per second squared, that's 32.2. Okay? So how many inches per second squared is that? So, no, well, it's just one inch unit. So you multiply it by 12, not 140. The seconds are the seconds. So it's about 386 inches per second squared. Make sense? All right. So if I take my unit weight and divide it by my gravity, I'm going to get density. So, and I'll go ahead. I've been lazy up until now. I'm actually going to put in my Greek letters, insert symbol. Go and insert that here, and then and you all get the units. I'll leave that off though. We'll say that divided by that. Whoop. So you're going to get a really small number for density. That's okay. Because we're talking about the unit weight of steel with these really large force units and really small length units, and then we're dividing gravity out. So it's going to be really small. That's okay. Is that all right? Okay. Because I don't want to hop back and forth, I'm going to copy and paste something. Just so I have that there. All right. You want me to give you all a minute to catch up? Okay, we got to take this and divide it by 12 cubed, right? Okay, so that gives us that. Now that's unit weight, and that's gravity. So we've got to, divide it out. So you'll get a small number. That's all right. Is everybody good? Anybody have any questions? Okay. Now let's take these one at a time. It doesn't matter which one you do first. We'll do the one we're familiar with. Let's do the stiffness matrix. So I'm going to put, let's see, let me box this in. Let's do a K matrix. You know me, I can't help formatting it up a little bit. All right, so you see the formula right here. I put the formula next to it so that we would have it. So this first term is 12 times EI over L cubed, right? Everybody see that? So EI over L cubed times 12, and then times 6L, and so on and so forth. So if I'm doing this first one, I might say what is it? Where'd my mouse go? Here we go. All right, so we'll say, was it E times I divided by L cubed times 12. Y'all should be good with that, right? All right. And then, let's see, going down, it's, what is it? It's not 12, it's 6L. 6L. Then we got minus 12. Right? Okay, and then we got 6L again, so. Right? And then that one is 4L squared. Put 4, and then that's L squared, and then minus 6L, gotta say, with the way that we set the lights in here, it's kind of tough for me to see it because down here it's pretty dark. All right, and then that's 2L squared. Oh. Change that. And then 12 again. Then minus 6L, so that was this one. And then 4L squared. And then what I'll do is, because I'm lazy, I'll just recognize that since it's symmetric, this term has to equal that one, this term has to equal that one, this term has to equal that one, and etc. Right? So we'll say equals that, equals that, equals that, equals that. Oh. So your stiffness matrix should look something about like that. I'll give you all a minute to catch up. Make sure you all are good with that. Maybe what I'll do is put something behind that. Oh. So that comes out a little more visible. Is that good? The way y'all can see that? I'll give you all a minute to catch up. Looks good. Did you all have like a stiffness matrix race? All right. Is everybody good? I'll give y'all a little bit longer. Are we good? You may go ahead and move on? All right. So let me go ahead and move this. I'll go ahead and move that there. Maybe we'll put this one in its place. So you crop that bottom part out a little bit. Y'all, let's see. How do I want to do this? So let's do this. Let's move that down there. Call that mass matrix. Whoop. Make it, I don't know, orange. Are you all okay if I cover this up here so that we can actually see what's going on? You okay with that? Is that okay? I'll move them both. I just want to make sure you all can see the formulas while you're working on this. Okay, so here's our mass matrix. Does anybody remember how we compute this little m? How do we do that? What's that? How do we compute the mass, the little m? There we go. So it's the density times the volume, right? So what's the volume of the bar? How do we calculate the volume of the bar? Area times length. So rho times A times L, that's M, right? So this first term, what I might do is I might say it equals rho times A times L divided by 420. And then all of that times 156. All right? And then just do the same pattern. Okay, so the next term down, that's 22 times the length. Next number down is, what is that, 54? Next number down is minus 13 times the length. Next number is 4 times L squared. Then 13 times L. Then it's minus 3 times L squared. Then it's 156, that works. Minus 22 times L. And then it's 4 times L squared. And then the same pattern for symmetric matrix. Should look something about like that. Let me collapse the decimals a little bit. We'll do that. Maybe what I'll do is this. Let me see if I can see if this works. Maybe I'll put that there or something. Oh, goodness. I lost it. There we go. So now you can still see the mass matrix, and there's your two answers. All right, I'll give you all a little bit to catch up because I want to make sure everybody's with me with what comes next. Maybe I can fit that down there. Oh. Bless you. There we go. I'll take this and maybe I'll move it up one. There we go. I can get everything fit on the screen. How are we doing? You got yours. All right. Everybody good? All right. Let me show you something. I'm gonna go back to the slideshow and review what the example said. Okay? The example said, determine the natural frequencies of the following beam and use one finite element. Okay? So what we just calculated was the stiffness matrix for an element. All right? Go back to the process of finite elements. We write a stiffness matrix for each element. We then assemble to get the stiffness matrix for the whole system. So for us, we would assemble to get the stiffness matrix for the whole system and the mass matrix for the whole system. All right? What do we then do once we've assembled? Ignore everything we're doing right now. When you do a finite element analysis, once you assemble your stiffness matrix, what's the next thing you do? Boundary conditions. So remember, 1 is vertical, 2 is rotational, 3 is vertical, 4 is rotational. Which rows and columns am I going to eliminate? 1 and 2. So what I'm going to do is this. Regardless of what I've got, I need to eliminate those. Right? Those are the ones associated with that fixed degree of freedom, right? And I've now got a reduced stiffness matrix and a reduced mass matrix. Make sense? So what I might do is over here on the side, I might say, all right, we'll call this KR, and over here, call this MR. And just set those equal. Excuse me. All right. Is everybody good? All right. Okay, can I delete these stiffness matrices and match matrices from the screen? I need a little bit of room. Can I go ahead and do that? All right, you all have the handouts in front of you, so. Okay. Now, let's go back to the slideshow for a second because I want to make sure we all have our eyes on the prize. This is our problem that we're trying to solve. This problem right here. And what we want to determine is an omega value. Now, let's go back to just fundamental eigenvalues. How many eigenvalues should we get for this problem? Our final matrix was what, 2 by 2? We had a 2 by 2 stiffness matrix and a 2 by 2 mass matrix, right? Like right here. 2 by 2, right? Okay, so how many eigenvalues do you get for a 2 by 2 matrix? 2. How many eigenvalues do you get for a 7 by 7 matrix? 7. All right, so we should get 2 eigenvalues, right? Okay, so what I have to do using Excel is I'm going to make a guess on an omega value. Then I'm going to compute this matrix. Then I'm going to take the determinant. So watch what I'm going to do. All right, so we'll call this an eigenvalue guess right here. All right, it doesn't matter what we put in this cell. Let's put in 10. It really doesn't matter. Okay, and I'm going to highlight that cell yellow so that I know we're paying attention to it. All right. Okay. Now we need to compute k minus omega squared times m, right? So what I'm going to do is I'm going to say it equals k minus this squared times that. Okay? Now, I'm going to hit F4 on this F13 to lock that in. In other words, when I copy and paste these cells, it's got to stay on that guess. Make sense? All right? So when I copy this out, like I look at this number, it's still fixed on the 10. What? K minus omega squared times m. Make sense? What? To lock it in, to make sure that, because watch what I'm going to do. Look, it's, all right, when I have this cell calculating, it's referring to this cell and this cell, right? Watch what happens. Let's just look at this. If I take this and I drag it down, it's now referring to this one and this one, but it's still locked there. You got to lock it in. That's what F4 is for. Make sense? Now, what do? I take the determinant of this, right? Equals m determ. Right? Let me give this another highlight. Let's make this, I don't know, red. And call this the determinant. Determinant, yep. Y'all with me? Does anybody have any questions? So watch what happens. I guessed a value of 10, right? What happens if I make that 20? It changes the determinant, right? What happens if I make it 30? Changes the determinant. What happens if I make it 60? It changes the determinant, right? I have to make that determinant equal to 0. So I go to Data, What If Analysis, Goal Seek, and I say I want to set the determinant, set cell K13 equal to 0 by changing that. And that's what I get, about 84.47. I want you all to come up with the same thing. You get it? Huh? Oh, and then it's K minus omega squared times M. Because, do you have your handouts on you, or? Oh. So. The what? There is no formula here. This is just a number. This. Again, it's just, that comes from here. That comes from this. Yeah, that comes from that. I'm basically calculating that matrix inside. Now, you told me there were 2 eigenvalues, right? I want you to tell me what the second one is. I'll give you a hint. It's much larger. What's that? Yeah, pick a big number. Like, say, 1,000 or something like that. You can, if you want, you can just copy and paste this cell somewhere else so you don't have to redo the formula all over again. While you're at it, let me write something down real quick. All right. Does anybody get the second one? Okay. Hold on. Let me see. I'm going to copy this down here. We'll call that omega 1, omega 2. I'm going to guess 1,000. We'll see what it gives me. Data, what if, goal seek. Oh. What if, goal seek, that. I get about 832. So your 2 eigenvalues should be about that. Yes. Oh, okay. Just do m_determ of that. Now, let me see. So if you make that like 60, so set that equal to 0 by changing that. Okay, you've got a formula somewhere or a value somewhere that's wrong, I think. Let me see. There you go. Something was wrong on your formula there. Try it now. What if goal seek set that equal 0 by changing that? Well, now 10.86. See, 84.47. Oh, That's what it is. You didn't, that has to be locked in at 4. See what I did?
Yeah.
So you have to lock that one cell in. Now let's try it. There we go. So now if I make that first value, let's say 10, what if goal 6 set that equal to 0 by changing that? There it goes. No problem. All right, let's see something. Let me see something. Let's see. So let me try to see something. Oh, that's a problem right there. That needs to be negative. I bet you that fixes it. Is this what you all are getting? All right. One thing I do want to show you, watch this. If you go back to the slideshow, remember I gave you this, the theoretical value? Okay. 3.52 times the square root, what have you. Y'all see that? All right, so I'm going to put theoretical, maybe box a little cell in right here. So what is that? It equals 3.52 times the square root of E times I divided by, what is that? Rho times A times L to the 4th. And look at that. With one finite element, we got a first natural frequency of 84.47. The actual answer is 84.17. Pretty close, right? Again, finite elements is an approximate technique. It is not the exact, answer. It's always approximate. But that's pretty good. That's pretty close. All right, everybody good? One thing I do want to point out to you, so this right here, these are your answers, right? These are your natural frequencies. But they are in radians per second. If you want hertz, an F1 and an F2, just take these numbers and divide them by 2 times pi. So maybe what I'll do is say that this is the be-all, end-all final answer for the problem. Right there. In other words, if I take this beam and I hit it with a hammer and let it vibrate, it will vibrate at a frequency of about 13.4 hertz. What? Just divide by 2 pi. Where are you at? Remember, okay, you say it equals that minus whatever your guess is squared times that. Then you got to lock that in. And then now you can drag and drop and take a determinant. Does anybody have any questions? Now, if you missed a step, no big deal. That's why I record these things. But I have got to do my diligence and show you a little bit of MATLAB if you don't want to do all this goal-seeking stuff. If I could find MATLAB. Hold on. There we go. Once it decides to load. I wrote out my matrices out here so that I could see them. Okay. Now, if I go into MATLAB, can you all read the font? Can you all read that? Okay. If I go in and actually just type out my stiffness matrix, and I wrote out the values right here, 10.875 minus 652.05. There's your stiffness matrix. There's K. And then M equals, and this is where things are going to get approximate because I'm typing in the numbers. What is it? It's like 0.0059, 0.00996, and then 0.21739. Okay, y'all see what I did? I just typed in my matrices. Now, if you use the eigenvalue command like we used last time, but you do this, the eigenvalue of K with M, that's the more generalized eigenvalue problem, you'll get this. Okay, now I know that the answer might seem to be a little weird because, you know, if you look at this, this is like 100,000, like that's not what we got, like 686,000. That doesn't make any sense. That's because it's giving us omega squared. If you take the square root of this, lo and behold. So, but okay, it says 828. That's a good point. But remember, I just typed these numbers in. You know what I mean? And it's not taking account of all the decimals. And keep in mind what Excel is doing is it's guessing. You know, it's iteratively guessing. MATLAB's actually computing it. So they might be a little different. Yeah, it's still pretty close, yeah. See, MATLAB isn't so bad, is it? Oh, I might show you all some programs later on. Oh, I've got some good ones. What's that? Oh, you should have seen some of the codes I wrote for my PhD. They were like 4,000 or 5,000 lines. Easy. Fun stuff. What's that? Did I sleep? Well, I didn't really understand what that word meant in grad school, so. I actually never used MATLAB as an undergrad. I just sort of picked up on it. You know, after a while, it's not bad. You know, there's probably some fundamental things that I could use a little work with, like plotting and getting my plots to look right is something I always need a little bit of work with. But in the end, I like MATLAB for when it works, you know, for using the right tool for the right job. I think in those cases, I like using MATLAB. All right, any questions? All right, I do want to at least introduce you to the topic that's coming next, which is stability analysis. In other words, buckling, which it's kind of funny. In steel design, we literally talked about this yesterday, so it's funny how the classes are aligned. I'm going to go ahead and give you this just so you have it. But I do want to give you all sort of a carrot for what comes next after this. So, this is the last analytical topic that I am going to have you do in this class. In other words, after this, no more Excel, no more of that stuff, okay? This is what I think is going to happen. What's that? No, well, yeah, but there's no final. This is what I'm going to do. We're going to talk about stability. In other words, buckling problems. I'm going to give you a homework assignment, your workout Excel homework assignment on vibration and buckling maybe sometime next week. It'll be due after spring break. At some point, I'll give you a take-home exam. It will not be during finals week. You'll have another week to do it. Then no more exams. The only thing left from then on is FE Map. I've been, talking it up a fair amount, and now I think after next week, we'll be ready to use it, actually employ it. No more of this Excel crap, The purpose of the last 9 or 10 weeks or however many weeks we've had up until now in spring break is to get you versed with the theory, get you understanding what this stuff means. Don't get me wrong, we could have 6 finite element courses here at Marshall. We could have finite elements 1, finite elements 2, and go through all sorts of stuff. We could do, thermal analysis and do all the math associated with that, and fluids analysis, and we do electromagnetism analysis. We can do nonlinear, and we could go on and on and on. There is a point, though, with this first level introductory course that I'm of the opinion that you know enough now that you can start opening these programs and using them. So what we'll do after spring break for the rest of the semester is use the software, and we'll have some fun. Do some real finite element analysis. Stuff that you all will do not only in a research setting, but when you get out of here and get jobs. Whether you're a structural engineer, mechanical engineer, geotechnical engineer, what have you. This stuff is how it's done nowadays. So I'm going to show you the fundamentals of it. And I think it'll be a lot of fun. This class will change night and day, okay, after spring break. So, and that's fine. What I'll do is I'll sort of close it off for now. The only thing I'll say is we're going to talk a little bit about buckling next. In other words, you've got a column like this. When does it buckle? And you're going to find that there are some damn close similarities between the problem we just did and this problem. And when I say close, I mean damn close. We will develop a new type of matrix with vibrations. We did a mass matrix. For this, we will develop what's called a geometric stiffness matrix as opposed to just a regular old stiffness matrix. And we do eigenvalues as well. The eigenvalues, though, will be the buckling loads. All right? Make sense? What? As I say, we literally just talked about this in steel design. And we talked about, how you get to this differential equation, and you say, well, exact same thing, yeah. But if you think about it, this differential equation is not much different than the one we did for vibrations. The second derivative plus a constant times u equals 0. What did we have for vibration? Let me go back a little bit. We had this, right? It's the same thing. There's a reason why these sciences and these fields are so close together. It's because the math is very similar. You're looking at different things, and that's this is where the fields are similar. After this, they sort of go like that, but they start off at a very common thread. Make sense? All right, that's all I have for you all today. I will see you all next time or next week. So you all have a good weekend. Remember, you all have a homework due Tuesday. I will give you all a homework then on vibration and buckling, and that'll be your last workout assignment. And we may have an assignment or 2 on FE Map. You'll have your project, and that's it. Sound good? All right.